Hello and welcome to another video. In this video we're going to be doing the last problem of the biweekly contest 122, and it's divide an array into subarrays with minimum cost 2. And in the problem you're given a zero indexed array of integers nums of length n and two positive integers k and distance. The cost of an array is the value of its first element. For example, the cost of 1 to 3 is 1, the cost of 3 for 1 is 3. You need to divide nums into k disjoint contiguous subarrays such that the difference between the starting index of the second subarray and the starting index of the kth subarray should be less than or equal to distance. Return the minimum possible of these subarrays. So the first subarray that you have has to start with this first index, kind of like if you did the first problem in this contest, but then the next ones can start wherever you want as long as the second and last subarray are at most distance 3 apart. So they kind of show you this first thing, so you can break it down into something like this. And then this is the second one, and this is the last one. So these are distance 3, so that is valid. And the sum here is 5. And in the second problem, you want 4 subarrays and distance is 3, so it looks like they want to break it down to like this, like this. So the last and the second subarray distance is 2, which is valid, and the total is 15 here. And for the last one, we want 3 subarrays and the distance needs to be 1. So you can do this. And this is going to be the best, and the distance here is 1 from the second and the last. And so this is 26, right? Maybe I can't count 36. Okay, so this problem is a little bit similar to the first one, but now instead of having 3 subarrays, you have as many as it asks, and also you have to have this like distance variable, and you have to do it pretty fast because the constraints are 10 to the 5th, so you need to do it in roughly like log n or n log n. And what I noticed for a lot of these like really hard contest problems, I mean, I don't know if this one's like really hard, but it is very common to have to do it in n log n by doing some kind of like binary searching or some kind of like optimizations. So it's very common to have the n log n solution. But regardless, let's look at something. So notice that if we have this array, like I said, the very first array has to start here, right? Like it can't start anywhere else. So the first chunk is going to start here, but now the second chunk can start wherever. So let's say we want 4 chunks with a distance of 3. Let's actually move this. So the second chunk can start wherever, right? Like there's no constraint there. But let's say the second chunk, let's say we just say like, okay, the second chunk, we'll just say it'll start here, right? This is like the second array. That means that the last array has to be at most 3 away from this. So if we just go 1, 2, 3, that means that the last array has to start here or somewhere earlier, right? It has to be in this range. So whenever this starts somewhere, you know where the range is. So basically you can think of it as a range query, and you can just say like, okay, well, let's just start here, let's say, and for this starting location, where's like the maximum the last number can be, it's going to be in this range, right? So something like one valid way you can do it would be like this would be the second array, this would be the third array, this would be the fourth array, right? Or like this as well would be valid, or any kind of combination here would be valid, right? So you can also do something like this, obviously, this would be fine, like anything here. But this is the range, and if you try to have the fourth element over here, now no matter where the third element is, there's going to be an issue, basically. So like I said, the third element location doesn't matter, so let's say it's here. This distance now is not 3, it's actually 4, right? Between the second and the last array. And so that's the problem. So basically you're asked, given some range, let's say we have this range now. Like, so if we can only pick subarrays starting at these locations, like let's say the second, third, and fourth subarray have to be in this range, what's the optimal solution? So the optimal solution, kind of similar to the first problem, is just pick the two, like the however many you need of these things, you pick the smallest ones, right? So the optimal solution would be pick the 3 smallest numbers here. like assuming we have to pick from here and we can't pick anywhere else, then our subarray 2 would be this. Our subarray 3 would be this. And our subarray 4 would be this. This would give us a sum of 3. So we're going to ignore the 3 because this is always going to be the same. But this will give us a sum of 7 plus 5 plus 2, which is 14. And if we try any other locations, those are going to be worse, right? Because then we'll include the 9. So basically, you can think of it as you have some range defined by distance. And the optimal indices, or the optimal numbers to pick, are the smallest k minus 1 numbers in that range. Because if k is 4, if we want 4 subarrays, we know the first one has to start here. So that we can't change. So really what we want is we want 3 more subarrays that are in some range. Now, like I said, if the second one starts here, then the last one has to start here. But the second one can start anywhere we want, right? So this range can be basically like a sliding window. So we can say, like, if the second one starts here, then where can the last one be? It can be anywhere in this range now, right? It can't be anywhere past this. So we could pick like this and this and this and so on. So basically what we can do is we can just have a range starting here, right? Like if our distance is 3, it's going to be this range here. Yeah, so I think I did do it correctly, but yeah. So if the second number is here, then the last number has to be here at the farthest, right? Because this would be a distance of 3. And then basically we can just move our window. So we can just say like, okay, we'll just take our window, we'll get some numbers here, and then we'll move it here. And we'll get some numbers here, move it 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 here. So what we want to do is we want to be able to do a couple things, right? We want to have a range, be able to get smallest k numbers in it in log or constant time, and be able to add and remove numbers from it in log or constant time. Right, because like our first range will be 7, 5, 9, 2, and then when we move it, then we want to get rid of the 7, add a 9, then we want to get rid of the 5, add a 4, and so on, right? And if we can do all these things, if we can get the smallest k numbers in it in logarithmic time, right, given a range, get this in log or constant time, and be able to add and remove numbers in log or constant time. And so if you notice one of my tabs, there's actually something in Python that I haven't used before that I was looking at called a sorted list, and this will let you do that. So let's take a look at some of these things in the sorted list. And basically a sorted list under the hood is implemented using a list and a tree. You can read up on it a little bit further. But essentially a sorted list is a list that is sorted, and you can add values in logarithmic time. You can update it. You can add like multiple values in k log n time. You can also initialize it in n log n time just by like getting an array and sorting. You can also remove values in log time, and you can do like bisect and things like that. Like bisect would basically tell you like if I was to put an element into here, where would it go? You can do that in log time. You can also pop from the end in one time, and you can pop from the middle in log time. So most of the operations on this list are able to be done in logarithmic time. So you can see pop is in log time, bisect is in log time, and so on. And also, if you want to check if something is in here, it's in log time. Because essentially, if you think about it, it's basically implemented, I think when I was reading it, it's like a tree of lists. So imagine you can just have like a bunch of lists that are sorted. So now if you put something in, if you have a bunch of lists and you put something in the middle of a list, now you're not shifting everything, you're just shifting like a small part. So that's why it's logarithmic. So basically all the operations are logarithmic, and this is going to be very useful. I think you can also do this using 2 heaps. But using 2 heaps is going to be kind of tricky. So instead, I'm going to use 2 sorted lists. There's also things called sorted sets in Python, which I don't think you can use here, but you can in C++. I think in C++ it's called like a sorted multi-set or something, which is like a set that contains duplicates, which is basically a sorted list, I guess. But yeah, there is also a, like I said, sorted set in Python that, your numbers are sorted, and then insertions and deletions are logarithmic, but here the sorted list is going to be better. So let's kind of walk through what our solution is going to be with a sorted list here. So the first thing we're going to do is we're going to start with, like, our initial range is obviously going to be just like the first chunk that we have, right? So the first chunk we have will just be distance plus 1 elements, because the first and last element have to be distance apart. So we can just get this chunk and we can sort it. So that would just be 2, 5, 7, 9. Now we need to get 3 numbers out of here, right? We want 3 out of these 4. So what we can do is we can actually have 2 sorted lists. And obviously for, like, if we have 3 in 1, it doesn't really make too much sense, but your numbers can get really big and your distance can get really big. So this can be like, like if the imagined distance is like 1,000,000 and k is like 500k or something, then you would have even sorting. But basically what's going to happen here is we want 2 lists. So we want one list of items we are using and another of items we aren't using. That way we want to be able to, the other thing I forgot to notice, we also need to be able to get, like, the sum of all our, like, we want to be able to get the sum of the min k elements, because let's say k is like 500 or something, or 1,000. We want to be able to, like, get the sum in constant time. And the way we're going to do that is we're just going to see what elements contribute to the sum, and when we get rid of an element, we'll just say, did it contribute to a sum? If yes, then let's subtract from the sum, and if it didn't, then it's not. And if we add the same thing, is it going to contribute to the sum? If yes, we'll add that one element, and if not, let's not. So first thing we do, like I said, we get a range, which makes sense, just from the second element up until distance plus 1, because, like I said, if the second element is here, then the fourth element has to be here. And this is just a generic case for, like, whatever k elements you have. If the second element is here, the last element has to be at whatever index this was plus distance. That's why you want distance plus 1 range here. So we sort it, then we break it down into 2 arrays, items we are using and items we aren't. So like I said, we want 3 items. We want the 3 smallest. So the 3 smallest, pretty easy. Now that you have it sorted, you just take the first 3, right? So the items we are using are going to be 2, 5, 7. And the one we're not will be 9. Then we know we're using 2, 5, 7 here, right? So we can just calculate a sum. So this sum is just going to be 14. And we're going to store that as our initial result, and we're going to try to minimize this. So our result will be 14, and we're going to try to minimize, and that would be the equivalent of using these 3 numbers, right? So that would basically mean the first array would be here, the second array. So we're using everything other than the 9s. The second array would be this. Third array would be this. And fourth array would be this whole thing, right? That would be the equivalent of 3, 5. So the 3 is always going to be there, but 5, 7, and 2. Okay. So now we basically need to shift our window. So we need to shift our window over here and then figure out, like, what are we going to use here? So what we need to do is we need to get rid of the 7. And so when we get rid of the 7, so like I said, in a sorted list, there is a method called just like in, so you can just say, like, item in list, and this is log time, because remember your list is sorted, so under the hood it just does like a binary search to see if the item is in there. So what we want to do is we want to check when we get rid of an item, is it in our list here? And in our case it is, right? Because the 7 is, like, we want to get rid of the 7. It is in our list. So we are going to get rid of it. Getting rid of an item is log n as well. Checking is log n. Look, basically all operations are log n in here. So, yeah, then since it did contribute to our sum and it was in the items we're using, we're going to take our sum. So this is our, like, best sum. Let's say our current sum is currently 14. So we're going to take our sum, subtract 7, because the 7 contributed, so now we'll have 7. Then because we need an item here, like we always need 3. We're gonna check, is there an item in this list that we weren't using? And if there is, then we're just gonna throw that in there, right? Because we need 3. So there is an item in here, so we can take this 9 and move it in here. And I'm sure you can optimize this a little bit to get rid of some steps, but this is kind of just what I was doing. So we put in the 9, and now we will update this to be 7 plus 9, or like this whole sum, right? So this is just 16. Then finally, we actually need to insert this new item, right? This is the new item we're on. We got rid of the 7, we need to insert the 9. So when we insert the 9, we check, do we actually want to use the 9? And it's going to be pretty easy for the sorted list, because basically for the item we're inserting, we just need to check, is it smaller than the last item in the items we're using? If it is, then we'll kick out the biggest item in the items we're using, throw it into the items we're not, and put in the 9. So the 9 is not smaller than this 9, so we don't need to use it, right? Because this is like, you can get the biggest item in the list in O of 1 because it's just like a normal, you can still index it normally. So we're going to put the 9 into the items we're not using, right? Because it's not smaller than anything in here, so we don't need to use it. So our current sum is 16 and our best sum is 14, so we're going to keep our best sum. Then we shift the window again. So we want to get rid of this 5. So we check, is 5 in our sum? Yes, it is. It's in our items we're using. So we need to modify this. Oh, I'm going to do that at the very end. So now that we got rid of the 5, we are going to add this 9, right? Because we need one more thing. So we're going to take the 9, put it in here. And now what's our sum? So our sum is 20. So we'll update it to 20. And remember, we got rid of the 5. Now we actually need to put in this 4, which is our new element for our new window. And so when we put in the 4, we're going to check, is the 4 smaller than the biggest element in our used array? Yes, it is. So we're going to take this 9, that's the biggest element in our used array, and we are going to shift it in here. And instead, we're going to add a 4, and it will keep it sorted because it's a sorted list. So we'll add 4 here. And then we'll calculate a sum. So this will be 13, 15. And is 15 smaller than 14? No, it's not. So really quickly, once again, I can show you what these arrays will look like if we use 249. So if we use 249, basically what's going to happen is we can use one of these 2 9s. It doesn't really matter which one. So let's say we use something like this. This will work. So 9, 2, and then this, right? And so the second and last array are a distance apart, right? Just like we want because we have this window, and this would be the arrays, right? 9, 2, and 4 would be your things you're using. So that's what that would look like. Okay, now we shift our window again. So we have to get rid of A9, and duplicates are pretty easy to handle in this case. So the way I had it in my code, at least, I just checked, is there a 9 in here? And it doesn't really matter where you check. Like, you can check in here or in here. It's going to be the same thing. So I checked in here, I think. But it doesn't, like I said, it doesn't really matter. So there is a 9 in here, so we're going to get rid of it. And now we need to fill up the slot, so we'll fill up the slot with this 9. So our sum stays the same. Then we also need to add in this 5, right? Because that's what we added. So we're going to check, is 5 less than 9? Yes, it is. In which case, the 5 will be better. So we're going to put the 9 over here and the 5 over here. And now our new sum will be 11. And once again, quickly to demonstrate this. So this would be an array of something like this. So pretty easy once you start doing a few of them. So this would be 2, 4, 5, right? And it satisfies the distance property. So that would be that. 11 is smaller than 14, so we'll update it. Then we shift our window again. So we got rid of the 2 and we put in a 2. So for just simplicity's sake, I'm just going to leave everything the same because we basically got rid of the same. Like, I can show where we're getting rid of it, but it's going to end up looking exactly the same. So this will be the same as well. And finally, we get rid of the 9. So the 9 is over here. It's not in our sum, so we're just going to get rid of it there. And we add a 6. So when we add a 6, we check, is 6 less than the biggest element in the items we're using? No, it's not, so we'll put it in here. So this doesn't contribute to our sum, and our sum is the same as it was. and that is indeed true, and our finals arrays would look like this. So we need to use 2, 4, 5, so it would be like this. This would be the 4 arrays. And so finally, once you get the minimum like 3 arrays you would use out of all these, right? Like whatever our original K was 4, but we made it 3 because we know the first element has to be here. So then you just return the smallest 3 elements that you found plus this thing here. So you would return, in this case, 14. And that would be your answer. And that's basically how you do it. So you have 2 sorted lists of items you are using, items you're not, and every time you add an item, you check, do I want to add it to my items I'm using? Like, is it going to make it better? If not, let me add it to my items I'm not. And every time I remove, you check, is it in here? If it is, remove it from here, and then fill up the slot from here. If it's not in here, then just remove from here. And yeah, like I said, I will link this sorted set or sorted list thing where it tells you all the functions in here. And yeah, and let's look at the code. So first thing I do, subtract 1 from K, right? Because the first element is fixed. Then, like I said, we get the first, like our initial numbers that is sorted. So that's just like if we want some numbers with a distance of 3, that means we want to get the first 4 numbers here. And so that's kind of what I do here. So I, distance plus 2, non-inclusive, and then I sort it. So I'm going to have an array of sorted numbers. And then I split this up into 2 chunks. Small nums is going to be the numbers I am using, and the large nums will be the numbers I'm not. So small nums will be every single number. We want the first K numbers, right? Or K minus 1. So if we want 4 chunks, we're going to have 3 numbers here, and then large nums will be every number after that. And because this is sorted, it's easy to do. You just split it into two chunks. Then you have a starting result, and you have a current sum. So your current sum will be the sum of the small numbers, because that's what you're going to be using, and your starting result will be that as well. Then we just loop, literally like I showed in this picture, like let's say our starting range is here, then we would loop from here all the way to the end to update our range, because the starting range is here. So this is what I made the starting result, the 3 smallest things in here, and then I would just loop from these numbers. Every time I loop to a new number, I update my range. Right, so my range moves 1, and I get rid of a number. So in this case, it'd be getting rid of this, and I add the current number, and then I move the range, and then get rid of another number and add the current number, and so on and so on and so on until we get to the very end. And then I just have a bunch of if statements. So I get the number I'm trying to remove based on the index I'm currently at, right? Based on like the length of your subarray, you can just figure it out with this equation, and then I just check. So I think I did do it the other way. So I said, if the number I'm trying to remove is in the numbers I'm not using, let's just get rid of it. Otherwise, I need to get rid of it from the small numbers. I need to decrement my sum appropriately, and I need to check if there are large numbers, then I will just take the smallest number. So I guess I didn't really show that in the picture, but let's say we have a bunch of numbers here, and let's say we are removing like this 5. So this large numbers obviously won't always have 1 number, but it'll be sorted. So let's say I have like 6, 7, 8, 9 or something. If I remove this 5, I will basically just always be getting the smallest number out of the large numbers. And you can pop from index 0, I believe, in O of 1, and you can pop from any other index in log n. Like I said, you can get rid of items from the middle in logarithmic time using this sorted list. So that's basically what I did here. So I just said, like, if I do have to get rid of one of the numbers I'm using, then do I have any extra numbers? If I do, let's just get the smallest one of those and add it into my numbers that I'm using. And then finally, the last part is adding the current element I'm on. So if my small numbers has an extra space, which sometimes it will, so sometimes you'll have a case like this where your small numbers will be like this, depending on the distance, and your large numbers will be nothing. And then when you remove, you will just like remove an element, and you'll have nothing in here, right? So then when you add, if this has an empty space, just add, you're always going to want to add in here. So that's what I check for here. If it has an empty space, just add it in there. Otherwise, if the number I'm adding is less than the biggest number in the numbers I'm using, then I just want to pop the biggest number out of the ones I'm using and add this number instead because it will be better, and take that biggest number in the numbers I was using and add it to the unused numbers. And like I said, just increment the current sum appropriately. So the way you do the current sum really quickly is you just figure out every time you remove a number, like what am I removing, and increment or decrement, and every time you add a number, you just increment or decrement by that one number. So you don't need to keep doing like a range sum query or anything. And so finally, the last case is if you're not adding to the small at all, then you just add to the large and your sum isn't affected. And you minimize your result. You just say result is the minimum of the old result and our current sum. And at the very end, you return your result plus num0 because num0 is fixed. So the sum I'm getting is every array other than the first one because the first one's fixed. Yeah. And so definitely would encourage you to check this out. This sorted container sorted list. Like I said, there's also a sorted set, which was used for other problems. I just never really bothered to use it because there were kind of like other ways you could do it. But I feel like for this problem, this is going to be the best way by far. And if you actually look at the solutions, most of them use this. This is language dependent, like I said. In other languages, there's other stuff. There's like a tree map or sorted multi-set or whatever. So this is going to be language dependent. In Python, this is what I would go with. You can look up whatever you want for another language. I think maybe in some, actually, there might not be stuff. Like maybe in JavaScript, not entirely sure. Yeah. And apparently we got a wrong answer. Okay, curious about that. Maybe I deleted something. Oh no, it does work. Weird. Okay. Yeah, I don't know why this test case failed then. Okay, yeah. So, and you can see it's pretty good. I was comparing it to other solutions. I think other solutions had about 2K runtime. Maybe I even, let's see if I have any of them saved here. If I go to submissions, I think I copied some of them. So yeah, they were around like 2K runtime, 2100, and this one was a bit faster. And yeah, if you look at solutions, most people, so I was looking at some Java, there's like tree sets in Java, as opposed to this this sorted list. But in Python, pretty much everyone was using a sorted list. And in C++, they were using some other thing, like two sets. I think in C++, there's like an ordered set that you can use as well, which is basically this, that can have duplicates. So whatever you want, yeah. Okay. Yeah, but that's going to be, oh yeah, let's actually go through the runtime here as well. I forgot about that. So like I said, all of these operations, like adding a number, checking if a number's in here, all these things are going to be logarithmic time. So this is going to be an nlog(n) solution. And the space is going to be O of n because the sorted list takes up O of n, and you have two of them. So but yeah, definitely would encourage you to use this. Kind of rare, but I did like, I think the thing you notice once you start doing these like really hard LeetCode problems is you learn a lot of new things that you basically never really used before, just because the problems are a bit tougher. So kind of cool. And if you did like this problem, please like it, please subscribe to the channel, and I'll be making the videos for the actual weekly contest in the next few days. So thanks for watching.